Good morning to all of you.
Uh, Sir, I have one doubt, sir, actually.
Yeah, you can ask. Yes, please.
Sir, yesterday, like in the assignment, in the seventh question, this is Arvind, sir, actually. First of all, let me
Yeah.
introduce.
Okay. Yeah. Okay.
Sir,
So seven
actually, I
is
had one doubt in that seventh question, sir. Like there were two differential equations. So, like with respect to one, we had to do the partial this thing, and like while deciding the integral functional, like we have to do the partial thing, or like we have to consider that another thing as constant, sir. Actually.
no. You have to because no the way the differential equation is given. So you need to consider basically the two-weight function. One would be corresponding to the first equation, and another for the second equation. And
Okay.
subsequent, when you go for the integral functional, the first weight function you can take as delta v, and because that is based on the force balance along the transverse direction,
Okay.
and the other equation is moment balance, so the weight function w2 you can take as delta theta. And when
Okay.
you are doing the integration by parts in the first equation, it is straightforward. Now you can one derivative can be transferred to the weight function, and
Okay.
similarly in the second equation, first term you will have to transfer one derivative to the weight function, and the
Hmm.
second term would remain as it is.
Okay.
Yeah.
Okay, sir.
So, are there any other questions? Okay, so then let me
Excuse
start.
me, sir. Excuse me, sir.
Yeah, good morning. There was some problem, so I'm back. So, is my screen visible? Hello, is my screen visible? Hello, am I audible? Okay, so I have unmuted you. Okay, so yeah, so
Good morning, sir. You are
yeah,
audible, sir. Screen is
yeah,
also visible.
okay, okay. So then let me start.
Excuse me, sir.
Yeah,
Sir, I have one doubt, sir.
yeah. Tell me.
Sir, while deriving the weak form of any differential equation, sir,
Yeah,
we perform integration by parts.
yeah.
Sir, can you please explain to what step exactly we have to do this? Because in some equations we have to do it twice and in some only once. So can you
So
please
yeah,
explain?
so see, basically the aim is to equally distribute the derivatives between the weight function and the unknown variable. So suppose if it is a second order differential equation, then it requires integration by parts only once. But if it is a fourth order differential equation, then you'll have to do the integration by parts twice to equally distribute the derivative between the weight function and the unknown variable in the integral term. So it depends on the order of the differential equation. So if the differential equation is nth order, then you'll have to do the integration by parts n by 2 times.
Sir, what if n is odd?
If n is odd, then in the integration by parts you have to do such a way that whatever boundary terms are coming, they should be meaningful. So meaningful in the sense that we should have ultimately we should be able to prescribe those boundary condition. The primary variable should be defined variable, and the secondary variable also should be variable which can be can be specified at the boundaries. So, of course, the integral functional can only be obtained if the differential equation is of even order derivatives, and if the differential equation is of odd order derivative, then you cannot obtain the integral functional. But of course, weak form can still be obtained.
Yes, sir.
Okay.
Sir,
Yeah. Yes, please.
sir, I had a doubt in how do we identify primary and secondary variables, sir? The concept behind identifying the variables.
So I had said no in the no when you get the boundary terms in the weak form. So boundary term would be consisting of product of two kind of terms. One would be involving weight function, and another would be involving the some constants of the problem and unknown variable. So the primary variable is you in place of weight function, if you substitute the variable, so whatever you get, that is the primary variable. So if there is only one boundary term which is involving only weight function, then the primary variable would be only the variable itself, say u or v. But if there are, let's say, two boundary terms, in one you have w in the boundary term, another you have dw by dx, then the primary variables would be say v and dv by dx. So that is, in place of w you write the variable, say v. So you get from one you get v, from the other you get dv by dx. So that is how you identify the primary variables, and then the coefficient of weight function in the boundary term is the secondary variable. So if there is only one boundary term, then there would be only one primary and one corresponding secondary variable. But there are two boundary terms, then there would be two primary variable and there would be two corresponding secondary variables. So if you would have seen in the assignment problem, the last question. So in that, actually there were, if you see, there are three boundary terms. But if you look at the first and third boundary term, both of them are involving weight function w. So actually these need to be combined together, because they are involving the same weight function w. So in one you have then w into, you will have d by dx ci d2v by dx square plus p dv by dx. So that has to be combined. So that will give you one primary variable, that is v, and the corresponding secondary variable would be the coefficient of w, and the second boundary term is dw by dx. So the primary variable would be dv by dx, and then the corresponding secondary variable would be ei into d2v by dx square. So that is how you identify the primary and secondary variables, just based on the boundary terms. Okay. So I think when I took the examples during the discussion on
Sir,
weak form. Yeah. Yes, please.
Shimi sir.
Yeah.
Sir, so in that last question, we have to multiply the first boundary term, the coefficient of first boundary term and third boundary term.
You have to combine them together because both of them are involving w.
Yes, sir.
Yeah, so it would be like w into then d by dx ci d2 v by dx square plus p dv by dx. So that would be the ultimately that boundary term. So in that the primary variable would be v and the secondary variable would be that the sum of two terms.
Yes, sir.
Yeah. Yeah. Any other question? Okay. So then let me start. Yeah, so we were discussing the finite element. So the last class, basically, I discussed many examples, although those are simple examples, but this can be extended. Whatever we are discussing can be extended to any number of elements, and whether the uniform cross-sectional area, material properties, or variable cross-sectional area. So it can be extended to different kinds of problems. So today I am going to discuss. So far what we have discussed is just we have a rod under the axial load, either concentrated or uniform load, and then we try to solve different type of problems. So we assume that the cross section is much smaller compared to length, and the stress, only non-zero component of stress is normal stress along length, that is sigma xx. All other stresses are zero, and independent strain is epsilon xx. And due to Poisson's effect, there would be epsilon yy and epsilon zz, and other shear strains are zero. So based on that assumption, we solved various problems. So now we can extend this to solving the truss structure problems. So that is what I am going to discuss today. So that is modeling of 2D. 2D means no truss structure. You know that truss structures are made up of the members which are only subjected to loads along their length. They adjust the loads and deformation through the longitudinal stiffness and load carrying capacity. They do not individually, the members are not subjected to any bending. The structure as a whole might be taking the transverse load, would be resisting the bending load, but the individual members of a truss structure are only resisting the loads by axial, the axial deformation and axial forces developed in the cross sections of the members. So that is what we are discussing, modeling of 2D truss structures. So when I'm saying 2D, because you could have 2D truss structures and 3D truss structure. So for example, if you know, you would have seen in airports, you would have seen the structure. So they are more like 3D truss structures. And but if you look at the maybe bridges, and also each side you will have a truss structure, so which is more like a 2D truss structure. So in the 2D truss structure, all the truss members are in one plane. So when we say 2D truss structure, means all truss members are in one plane. So now we are going to use the same element, because the truss structure, as I said, the members individually are undergoing deformation along their length, and they are resisting the external loads by the axial stresses, that is normal stress developed along length of the member. So we can use the element which we have developed, the the two noded or three noded truss element, we can use for modeling these problems. But there is an additional problem, so let me just take a simple example and then demonstrate you that what are the problems. So suppose we have this as one member, and this is the another member, and see they are the two ends are supported like this. And here I am assuming that there are only concentrated forces at the joints. So let us say this load is P1 and this load is P2. So these are the two members. Now this is the simplest thing now I am taking, and the same methodology can be extended to any 2D truss structure with any number of basically members. So now for modeling this, we model each member of a truss structure using one two noded truss finite element. So we take one element over here, and similarly this is the second member. This is also modeled using only one element. And as you know, in the truss structure, we have developed the element formulation taking the local coordinate with the origin along the first at the first node, and the coordinate direction capital X was along the length of the member. So this would be X, and this will be node number one, and this would be so this is node number one, and this is node number two, local node number two, and this is element two. So obviously for the structure as a whole, of course, you will have global node numbers 1, 2, and 3. But if I just talk of the second element, then this would be, let's say, local node number 1, and this would be local node number 2. And for this element, the element x-axis is going to be like this. And if you look at the degrees of freedom, so the degrees of freedom for the first node of the first element, we will have displacement along length of the member. So that is u at first node for the first element would be like this. Similarly, if you look at the second node, so the second node we will have the degree of freedom in this direction. So that would be u21. So the direction of these degrees of freedom are along the for the first element along length of the element. This is also along length of the element. When you look at the second element, so second element the degree of freedom would be u12, and no this for the second node of second element would be u22. So these are going to be the degrees of freedom. Now the problem you would realize that at the no then the the starting node of the first element or in the node of the second element, there is no problem, although the displacements are along no different directions, but they are only no one contribution from only one element. But if you look at node number 2, so you have no the u21 from the first element, this degree of freedom is in this direction, whereas the other degree of freedom is in the other direction, no, in this direction. So the displacements are in different directions element wise at no the common node, this particular node which is shared by both the elements. Similarly, if you look at the nodal forces, so the forces would be like here it would be q1 no the direction, let me, so as you know the force is in the here in the other direction, so q11 is going to be in this direction. Similarly for this element, if you look at no the node 2 for the first element, this would be q21, the direction of this force, whereas for the second element this would be q12, and no in this direction you will have of course q22. So the forces also at node 2, the common node shared by the element 1 and 2, are in different directions. So we cannot really do the assembly. So before we do the assembly, what then we need to do is we need to transform the element label governing equation into a common coordinate system, that is displacements and forces in a common coordinate direction for all the elements, and then we can assemble them. So that is what we do actually. So let us say we take the global coordinate system as small x and small y, and so first we have the element level governing equation in the local element coordinate system, then we transform in terms of the global coordinate system x and small x and xy for both element 1 and element 2 or any number of element in a actual structure, and then we assemble and impose the boundary condition and solve the problem. And when we come back to post processing, then again we get back the displacements in the local element coordinate axes, and then work out the stresses, strain and stresses in the element. So that is how we solve such problems. So let us say this angle is alpha. So what I have explained is, let me just write. So the observations from the way I have listed over. So the problems we did so far earlier, no, the assembly and all we did. So in that we had a member which is, was only in one direction, and we modeled that into two or three elements, and we assembled them because all the elements were in the same direction. So the local x-axis was same. So all the element level governing equations were in a kind of same coordinate direction. But now here, because the members of the truss structure are oriented in different directions, although in a common plane, so we need to transform the equations of motion. So the observation from this discussion is that each element has each element has a different orientation of local coordinate x-axis. So that is one. So because no, as far as the element level formulation is concerned, we will have to take the local x-axis, that is capital X-axis, on along the length of the element. So for the first element it has to be like this. For the second element it has to be like this. So obviously we see that they are oriented in different directions. So that is one. And the that's the coordinate direction. Similarly the degrees of freedom. So if I write the degrees of freedom, so in this case only, of course, the displacements along the length of the element at node, starting node and end node. So degrees of freedoms, so sometimes we simply write DOFs. So and nodal forces, so that is Q11, Q21, Q12, Q22, and so on. So similarly, and nodal forces are of nodal forces of connected elements. So we are interested more where the two or more elements are connected. Actually in a truss structure, at a point, no, at a joint, there can be more than two members also may be connected. So then in that case you will have three different elements and three different local x-axes, and the displacements, all of them have to be converted into a common coordinate system. So degrees of freedom and nodal forces of connected elements are in different directions, at common nodes. So this is the observation which I just explained. So now as I said, no, so therefore first we'll have to bring them into a common coordinate system. So that is before we can assemble all the equations. So then therefore for assembly element label governing equations, element label governing equations need to be transformed into a common coordinate system, into a common coordinate system. Often we call this as global coordinate system. We call this as global coordinate system. So let me first then demonstrate how we do this transformation into a common coordinate system. So let me take any element E. Of course, this is member of a 2D truss structure, so all the members would be in a plane. So if I consider any element E, and let us say that that is the element, and it has two nodes, 1 and 2. These are the node numbers, and the local x-axis is this, and the global x-axis is, let us say, this, and this is the y-axis. The angle between local x-axis and the global x-axis is alpha, And the displacements, if you look at, so we are saying that the displacement along global x-axis of node 1 is, let us say, u11, and displacement along global y-axis at node 1 is, let us say, v11. And similarly at node 2 you will have u2 of no element, no, rather than saying 1, let me say the e, because it's the eth element, so I'll just say e here. So v1e, and similarly this is u2e, and this is v2e. So these are the displacements in the global coordinate system. But as for the local system, the way we develop the first the equation, so here this would be u11, and in this direction this would be u22, small u. So that is small u, u11, and I think instead of yeah 1, and let me put that also as e, and this would be not 2 but u2e. And the similarly the forces also we are going to write in terms of the finally global coordinate axis. So here the force is q1e, and here the force is q2e. So these are the notations we have already used. So you know that the element level governing equation in the local coordinate system for two noded truss element is ea by l. L is the length of the element, and this is 1 minus 1 minus 1 and 1, we have derived this. And this side we have the degrees of freedom in the local with respect to local coordinate axes, and there is no distributed force small q equal to 0, so there are only the internal forces. So you have minus q1e and you have q2e. So this is the element level governing equation. Say this is equation number 1, let us say. Now as I said, so this is the procedure to develop this equation. We have already learned that if we have no local x-axis capital X along length of the element, then how to write the the integral functional, how to assume the approximate solution within the element in terms of as a function of capital X, and substitute in the integral functional, then take delta I equal to 0 and develop the element level governing equation. So those steps are the same. So this is the ultimately the element level governing equation with respect to local coordinate system. But now what we want to do is, see this no, the left hand side and the right side, so when you multiply these two, so it gives you the force along the local x-axis at node 1 and 2. Similarly these are the forces along local x-axis at node 1 and 2 of the element. So we need to do both, that is we want to express this displacement in terms of global displacements. So that is no u1e, v1e, and u2e and v2e. And also we want to express the forces also along be in terms of components along the small x and y axes. So what we want is we want to express, so we want to write this u1e and u2e, that is the elemental degrees of freedom with respect to local coordinate system in terms of global degrees of freedom, global in terms of degrees of freedom along the global coordinate system, in in terms of degrees of freedom along global coordinate system. So how we can do that? So suppose no, you wanted to write no this u1e, this u1e. So what we can do is no, we will have component of this capital u1e along this capital X direction, and similarly we will have component of this v1e along the capital X direction. So the component of u1e along capital X direction would be u1e cos alpha, and the component of v1e along capital X direction would be, because this angle is alpha, this would be 90 minus alpha, so cos 90 minus alpha would be sin alpha. So you would be able to write u1e is equal to this capital U1E cos alpha plus V1 no E V1E into sine of alpha. So the we are just taking the component, no, the component is capital U1E along capital X axis, and the component of this capital V1E along capital X axis. So U1E cos alpha plus V1E sin alpha is actually going to be, that is what is your U1E, small U1E along the capital X axis. So this is as far as the first node is concerned, and same thing you can do for the second node. That is, this angle is alpha, so we will have component of U2E along this direction, and we will have component of this V2E along this direction, and the sum of the two components would give you U2E. So similarly, I can write U2E is equal to capital U2E cos alpha plus capital V2E sin alpha. So you can write these equations. So because we have in equation 1, no, the equation is in terms of products of matrices and vectors. So we can write no this equation as in the form of matrix vector multiplication. So I can say U1E U2E vector is equal to this cos alpha sin alpha, because alpha we would know what is the orientation of a particular member of the truss structure. So we want to keep this as a matrix here. So cos alpha sin alpha 0 0 we will have, and then 0 0 again cos alpha sin alpha, and here we are going to have now the degrees of freedom in terms of displacements along global coordinate axes is small x and small y. So we will have U1E, we will have V1E, we will have U2E and V2E. So you see when you multiply, so this is 2 by 1 and this is 2 by 4, this is 4 by 1. So that this matrix we call as a transformation matrix consisting of cos alpha and sin alpha. So as you know, this we have already denoted earlier as DE. So DE is equal to this we are denoting as T, and this other vector I am calling as capital D. So this D is this, T is this matrix, and D is this vector capital DE. And let us say this is equation number 2. Again, this is 2 by 1, transformation matrix is 2 by 4, and this is 4 by 1. So now we are writing the displacement along the global x axis, the local capital X axis, in terms of the displacements along global x and y axis, that is u1e, v1e, u2e and v2e. U1 and capital E1 and capital V1 are the displacement degrees of freedom at node 1 of the element, and U2E and V2E are the displacement degrees of freedom of node 2 of the element, the second node of the element. So this T we call as a transformation matrix. So this D already know where we have defined this, and you see this T is the transformation matrix, because it gives the relationship between the degrees of freedom in the local coordinate system and degrees of freedom in the global coordinate system. And you can say this capital DE is the vector of elemental degrees of freedom in global coordinate system. Vector of elemental degrees of freedom in global coordinate system. Yeah. So now what we want is this equation 2 we want to substitute in equation 1. So then once we do that, we will have the equation in terms of displacement along the global coordinate system. But the forces will still be, so I can know I have this equation 2, that is small d equal to T plus D. So what we have, this equation E is equal to this. So in place of this I can write T into capital D. So then the displacements will become in the global coordinate direction, but the forces, the products will still give us the forces along the local x-axis, that is capital X-axis. So we also pre-multiply the whole equation by T transpose to transform these forces, right? These forces in terms of components of the forces along global small x and small y axes. So we do two things. So that is substituting equation 2, substituting equation 2 in equation 1, and also to transform the forces we pre-multiply. So pre-multiplying the resulting equation whatever we have after substituting small d from equation 2. So whatever equation we get, that I am calling as resulting equation, so we multiply that by T transpose. So this is T is transformation matrix and superscript T is for transpose. So then we will get, so you will see that we will get because we are pre-multiplying by T transpose, so we will have T transpose, and in between we have this element level stiffness matrix Ke, and then small d we are writing T into capital DE. So we have this small k into small d. Small d is written as no capital T into capital DE, and we are also multiplying it by T transpose. And the right hand side, because we don't have a small de, we will have only q. So we multiply it by T transpose because the whole equation has to be multiplied by T transpose. And the vector of consisting of q1 and q2 we call as internal load vector. So we will have this F1, yeah, no, this E. And now we call this as, let us say, if you look at, no, this is known as now the stiffness matrix, in terms of global coordinate axes. So we denote it by, let us say, Ke bar into De, then is equal to right hand side is, let us say, F internal E bar. So now T transpose it, T is, no, I have already said this is 2 by 2 and T is 2 by 4. This is a 4 by 1 vector. T transpose would be 4 by 2. So the Ke bar, which is T transpose K into T, will be a 4 by 4 matrix. And D is a 4 by 1 vector. Similarly, this T transpose is 4 by 2 into 2 by 1. So we'll see that no, this F internal E bar will be a 4 by 1 vector. So now this is the transformed equation. Say we call it as equation number 3. So now here you can say where this Ke bar is nothing but T transpose into Ke into T, and F internal E bar is equal to T transpose into F internal. So now this is the equation we have got. Now you will have to keep in mind that when we I have introduced this angle alpha. So the angle alpha, when I have taken this, so we measure basically, this alpha. As I said, it is the angle between the global x-axis and the local x-axis. For each element, this angle alpha is going to be different. So this is for a particular element, as I said. So this is measured, is the angle between small x and capital X, and measured along basically positive about positive z axis. So when you say this alpha, so is the angle between, it's already indicated, is the angle between small x axis and the capital X axis. So measured from small x axis, which is the global x axis, about positive z axis. So, and know in this case, because small x and y are like this, so z axis would be coming out of the screen. So we are going from small x to capital X about, the in this case anti-clockwise direction, that is about positive z axis, and that is how we would be measuring this alpha. Now let us solve the same problem which I just started with to explain you what are the associated problems. So let me simplify this little bit. I want to solve the complete problem. I am taking simpler examples so that it can be done in the class. More complex truss structures have to be, of course, analyzed. Either you develop your own, let's say, code in MATLAB or any programming language, or use a FE software like ANSYS, Abacus, Nastra, NISA. So you can use any of the software, you can create the geometry. So each truss member you would be creating as a line, and then you will be meshing each member using one two noded truss element, and then you would be applying the forces at the nodes and the boundary condition, and then you would be solving. So result would be displacements of all the nodes and the forces in each element, and therefore truss member, and then you can get the stresses. So I will demonstrate you all the steps, taking a simple example. So let me take the same example, only thing is I will make it more symmetric. So the same two truss structure. So of course all the joints are pin joints here. So in the reality, when you make these structures, so you make them such a way that at a particular joint all the members are basically uh, concurrent, so they are passing from the same point. Now when you extend, so all the members should pass, the extension of all the members should pass through the same point at a particular joint, and that is what you know call as a truss structure. So the forces are same. Let us say at this node you have these two forces, P1 and P2, and these are the two forces, and the global node numbers are 1, 2, and 3. So these are the global node numbers. Elements are, this is element 1, this is element 2, and the global x-axis is this, global y-axis is this, and let us say the angle between the first member and the global x-axis is 45 degree, and similarly let us say this angle is also 45 degrees, and the Young's modulus and the cross-sectional area is EA, length is L. Similarly for this member, Young's modulus and cross-sectional area is EA, and the length is L. And as you know, the local x-axis for this element is this, and local x-axis for element 2 is going to be that. So now we need to first transform the element level governing equation. So now if I look at the element 1, the first element 1, so you see alpha is the angle between global x-axis and the local x-axis. Local x-axis we are choosing as this, so you see the alpha is actually 45 degrees. So for this case, if you look at the transformation matrix T, it is cos alpha sin alpha, so 1 upon root 2, 1 upon root 2, because cos 45 and sin 45 both are 1 upon root 2, 0 0, and then you will have 0 0 again, cos alpha and sin alpha, so 1 upon root 2 1. This is going to be the transformation matrix. So if you look at the transformed stiffness matrix, so this Ke bar transformed stiffness matrix, we have written already T transpose into Ke into T. So this is the formula we wrote. So let me write it in terms of alpha, so that for the second element also I just put the value of alpha and get the transformed stiffness matrix. So now T transpose, so you know T transpose is this cos alpha sin alpha 0 0 0 0 sin alpha cos alpha and sin alpha. So its transpose would be cos alpha sin alpha 0 0, and then 0 0 again cos alpha and sin alpha. So this is T transpose, and Ke we already know it is EA by L in the local element coordinate system, 1 minus 1 minus 1 and 1, we have derived this, and then into T, T is again cos alpha sin alpha 0 0 0 0 cos alpha sin alpha. So you are just putting these values. EA by L I can take outside, so I can write here EA by L, and then if I multiply the first these two, this and this, A by L I am taking on the left hand side. So if I multiply this, so see we will get first, if I multiply this row with this column, so I will get over there as cos alpha, because second term is 0 here, so that doesn't come. When I take now the second row, so I will get now if I take the first one, I'm getting cos alpha. If I take the multiply with the second column, the same row, this particular row, I will get minus cos alpha. So similarly, when I take the second row from here and multiply the first and second columns, I will get, you can see, I will get sine alpha and minus sine alpha. Then similarly, when I now take this, so the third row with the first column, so we will get minus cos alpha and cos alpha. When similarly take the fourth row, that is this row, multiply with the first column, we will get minus sine alpha and sine alpha. Into this t is already there, cos alpha sine alpha 0 0 0 0 cos alpha sine alpha. So this is there. So now if you multiply again these two, so you will get EA by L, and now you will get a 4 by 4 matrix. So if you look at, the multiplication is straightforward. So first term will become uh, cos square alpha cos alpha sine alpha, and then minus cos square alpha minus cos alpha sine alpha, and then here we will have sine alpha cos alpha sine square alpha, and then minus sine alpha cos alpha minus sine square alpha. So this is what you will get. Here you will have the third row, cos square alpha minus cos alpha sine alpha cos square alpha cos alpha sine alpha, and then here we'll have minus sine alpha cos alpha minus sine square alpha, and then sine alpha cos alpha into sine square alpha. So this is finally the transformed stiffness matrix. This is a 4 by 4 matrix. This is what you will get as the transformed stiffness matrix. Now for the given case, now you can say that for the given, the element number 1, this Ke will be equal to maybe class only. So this Ke would be equal to, for the element 1, alpha is 45 degrees. So cos alpha is 1 upon root 2, sin alpha is 1 upon root 2. So if you put the values, so you are going to get cos square alpha as 1 by 2, cos alpha sin alpha also as 1 by 2, and sin square alpha also as 1 by 2. So you will get 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2, and 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2, and then minus 1 by 2, minus 1 by 2, 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2, 1 by 2, and 1 by 2. So this will be the transformed stiffness matrix for the first element. So similarly, now if you look at the transformed internal load vector, so F internal E bar will be equal to T transpose into F internal, and T transpose is cos alpha 0 sin alpha 0 0 cos alpha 0 sin alpha. So you have this into elements of this q1 e. So e is 1, so I let me write now, because we are talking of a first element, so let me put the element number. So this is q1 1 and this is q2 1. So if you do this multiplication, you will get a 4 by 1 vector. So as you see, the first one will give you minus q1 1 cos alpha, second one will give you q11 sin alpha, and then you will have q21 cos alpha and q21 sin alpha. And if you put the values of cos alpha and sin alpha, so you will get minus q1 1 divided by root 2 minus q11 divided by root 2, and then q21 divided by root 2, and q21 divided by root 2. So this is the transformed load vector. Now, so this is for the element 1. Now if we go to element number 2, so element number 2 means, if you look at now alpha, we have to identify alpha. So alpha is the angle between local x-axis and the global x-axis, measured along basically the positive z-axis. So at this node, as you know, the global x-axis is this, and this is the global y-axis. So actually alpha is going to be basically this angle. Now this angle which would be 360 minus 45. So you can also write no alpha as minus 45. So if you just take this angle, it will be minus 45 as per the sign convention I mentioned. So for the element 2, alpha would be equal to minus 45 degrees. So either minus 45 degrees, or you can say this is 360 minus 45. So either you use 360 minus 45 or minus 45, both will give you the same transformation matrix. So now if you look at this Ke bar for the second element, so if you put the value of alpha as minus 45, and then because this is already in terms of alpha, so you can just put the values of alpha over here. So in this, if the alpha is minus 45, then cos alpha would be 1 upon root 2, but sin alpha would be minus 1 upon root 2. So when you put those values, so you will see that Ke bar and the product of Young's modulus and cross sectional area is same for the second element also, although in general they could be different. We are taking right now length of the element also same, but they could be different. So this would be A by L, and you just put the value of alpha is minus 45. So you'll get this as 1 by 2 minus 1 by 2 minus 1 by 2 plus 1 upon 2, and then minus 1 upon 2 1 upon 2 1 upon 2 minus 1 upon 2. Just putting the value of alpha as minus 45 degree in the expression we derived already. Then we have minus 1 upon 2 1 upon 2 1 upon 2 minus 1 upon 2, and then 1 upon 2 minus 1 upon 2 minus 1 upon 2 and 1 upon. So this is the transformed stiffness matrix in the global coordinate system. Now in this, the displacements are also in the global small x and small y axes, and the forces are also in that same direction. So similarly, the F internal for the second element would be equal to, now you're putting cos alpha as 1 upon root 2, sin alpha as minus 1 upon root 2. So you'll get minus q1 2. That's now for the second element. So by root 2, as because next is sin alpha, so minus minus becomes plus. So q1 2 upon root 2, and then you will have q2 2 upon root 2, and then minus q2 2 upon root 2. So yeah, this is what you get as the transformed stiffness matrix for each element, for element 1 and element 2, and the transformed internal load vectors in terms of the global coordinate system. So now once we have this, we can do the assembly. Hello, am I audible? Yeah, so I think yeah, since there was no response in between, so I just want to confirm that you are all listening to me. Hello, am I audible? Okay. So yeah, and if you have any doubts and question, no, you can stop me anytime and ask the questions and doubts. Yeah, so once we have this transformed stiffness matrix for each element, and see this procedure is general, we can have any number of members in a truss structure. You will have to get the transformed stiffness matrix and internal load vector identically to any number of elements, and the then assembly is also no, similar. So now when you do the assembly, yeah.
Yeah. So then we are talking specifically about the elements and instead of
I
writing
think no,
values
your
one,
voice,
voice,
I'm not able to hear you.
hear you.
I'm not able to hear you. I think a lot of noise is coming.
Can you hear me now, sir?
No, I'm not able. I think there are a lot of
There are a
noise.
lot of like, so can you hear me now,
No,
sir? No.
yeah, no. Other thing is that you can write your question on the chat box, so I can see from the chat. Yeah, so I know if you have, if you want to ask something, your since a lot of noise is coming, you can write your question in chat, and then I'll see and discuss. So meantime, let me continue with the assembly. So what I'm saying is, now the assembly. So EA by L is common. no, for all the both the elements 1 and 2, because that is how we have taken the properties, although that is not necessary. And now since each node has got in terms of global coordinate axes two displacements, one along small x direction and one along small y direction, global x and global y. So and there are three nodes, total nodes are three, and each node we have two degrees of freedom now in terms of global coordinate axes. So we will have total 6 degrees of freedom. So the assembled stiffness matrix will be of size 6 by 6. So this is what we will have, 6 by 6 assembled stiffness matrix. And then we have no, this displacement vector, and then on the right hand side we have this load vector. So those displacements are now I am going to write. So in terms of global coordinate axes, so u1 the displacement along small x direction at node 1. No, so superscript I am removing, I am writing in terms of global node number. So it would be u1, then v1, and then the second node is u2, and the displacement along y direction is v2, and then the third node u3 and v3. So these are the displacements u1 v1 at first node along this is a small x direction, this is small y direction. Then you have u2 and v2 at node 2 along small x and small y direction, and these are common to both, because these are same for both the elements 1 and 2, u2 and v2, capital u2 and v2, and this is at node 3 u3 and v3. So now we bring in the contribution of first element. So as you see, the first element is defined between global nodes 1 and 2, and corresponding to those nodes degrees of freedom are this u1 v1 u2 and v2. So the contribution of first element will go to the first four rows and columns. So first four rows and columns means first element we will add into the first four rows and columns. So 1 by 2, 1 by 2, minus 1 by 2, minus 1 by 2, first row. Then the second row is 1 by 2, 1 by 2, minus 1 upon 2, minus 1 upon 2. Then the third row will go to the third row of the uh, uh, global stiffness matrix, assembled stiffness matrix, 1 by 2, 1 by 2. And then we have the fourth row 1 by 2, minus 1 by 2, 1 by 2, and 1 by 2. So this is the contribution of first element. Now when you take the second element, so the second element is defined between global node numbers 2 and 3. Corresponding to node 2, the degrees of freedom are these u2 and v2, and corresponding to node 3 are u3 and v3. So these will be corresponding to variable number 3, 4, 5, and 6. So the contribution of second element will go to basically third, fourth, fifth, and sixth rows and columns. So we will start with third row and third column. So that is the first element. No, the first that is this particular value of second element will go to the third row and third column, and then identically no you are. So this is the third row, third column. So there is already value here. So I will add here 1 by 2. Then here it would be minus 1 by 2, and then minus 1 by 2 and 1 by 2. Then we will go to the fourth row. So we have minus 1 by 2, plus 1 by 2, and 1 by 2, and minus 1 by 2. Then we'll go to the fifth row and third column. So minus half, half, and half, and minus half. And then the sixth row starting with the third column. So half, minus half, minus half, and half. So this is the contribution of the second element stiffness matrix. So wherever we don't have anything, we will put 0 there. So it would be 0 here. Similarly 0, 0, 0, 0 over here. Now if you look at the right hand side, so the internal load vector first element will go into first four rows. So we will have minus q1 upon root 2, minus q11 upon root 2, and then we will have third row would be q21 upon root 2, and then we will have q21 upon root 2. So this is a contribution of first element. Now the second element q, the internal load vector is this. So this will go to the third row, this will go to the fourth row, this will go to the fifth, and this will go to the sixth row. So if you know, you will have to add here. So here we will have q12 upon root 2, q12 upon root 2, and here we will have plus q12 upon root 2, and then we will have q22 upon root 2 and minus q22 upon root 2. So that is you are adding the contribution of no, the second element. So this is, let us say, equation number 4. So once we have done this assembly, then no, we talk of now the boundary conditions. So now this is assembled. So this is the global stiffness matrix, and now this is the vector of global degrees of freedom, and this is the vector of global internal load vector. So now if you look at the boundary conditions, now the boundary condition for the finite element assembly, what we have. So the boundary conditions are, now if you look at the structure we are considering, that is this structure, this one. So this node is, this is a pin boundary condition, so it is pinned. That means no, this node, global node number 1 is not allowed to move along x direction, and also it's not allowed to move along y direction. So therefore the displacement along both small x and small y directions would be 0 at node 1. Similarly at node 3 it is pinned. So pin means it is not allowed to move along x and small y directions. So u3 and v3 would be equal to 0. So that is one boundary one boundary condition is that u1 is equal to 0 and v1 is equal to 0 at node 1, and at node 3 we have u3 equal to 0 and v3 equal to 0. So these are 0. And additionally, now we will see that at node common node 2, that is this q21 upon root 2 minus q12 upon root 2, this would be actually force along the global x direction. And similarly this q21 upon root 2 plus q12 upon root 2 will be force along global y direction. So additionally we will have this q21 upon root 2 minus q12 upon root 2 is equal to p1, and the fourth is q21 upon root 2 plus q12. So subscript is node number and superscript is the element number. Just to remind you, this will be equal to the force along global y direction. So that is equal to p2. So these are the boundary condition. How do we get this? So particularly I want to show you that how do we get this. So suppose now if I draw the free body diagram of each node. So no, I want to show you that. So I think you should be clear about the free body diagram and everything. So basically, now if you look at the structure again, let me draw that structure what we are considering over here. So this is node 1. Actually there would be two reactions here. So let us say those reactions forces are R1 and R2, and here at this node there are externally applied loads P1 and P2. P1 P2 are known forces, and the reaction at, so this is global node number 1, global node number 2, global node number 3. Here we'll have, let us say, reactions are let me call them as R3 and R4. These are the reaction forces. Now if you element wise, if you look at each element, so element in terms of local element coordinate system, this is q11 and this is q21. And similarly if you look at the second element, so this is q12 and this will be the q22. So these are the forces. Now if you draw the free body diagram, FBD means free body diagram of node 2. So this is node 2, and there are externally applied forces here P1 and P2, and then no, in this no, this element is going to exert a force at node 2. So because no, this force is in this direction, so opposite of that will be this. So this will be q21, and similarly opposite of this force is going to exert at going to be exerted at node 2. So this will be in the, this will be q12, and these angles are 45 degrees, that we already know. This angle is 45 degrees. So now the coordinate, global coordinate axes are, this is x and this is y. So now if you do sum of force along x direction is equal to 0, the equilibrium equation along x direction. So one force is P1, and then this will have a component along small x, and this also will have a component small x. So we will have plus Q12 upon root 2, and this will be along the this component would be along negative x direction, so minus q21 upon root 2, it will be equal to 0. So therefore from this equation you can say that q21 upon root 2 minus q12 upon root 2 is equal to p1. So this is what one of the boundary condition I have written. So this one, so this comes from the basically equilibrium of node number 2. So that is some of the forces at node number 2. Similarly, for the same node, if we write sum of forces along y direction is equal to 0, taking forces positive along the positive y direction, so we will have one force is P2 along y direction, and then both these are going to have component along negative y direction. So we will have minus q12 upon root 2 minus q21 upon root 2 equal to 0. So therefore, I know you can say that q12 upon root 2 plus q21 upon root 2 is equal to p2. So that is what the other condition we have used. So I just want to know explain you each and everything, how we are getting this. So this comes from the equilibrium of forces along x direction at node 2, equilibrium of forces along y direction at node 2. So we are able to express these internal forces, combination of these internal forces in terms of P1 and P2. These are externally applied known forces P1 and P2. So in the truss structure, these are the concentrated forces which are acting. Similarly, these terms, these can be written in terms of reaction forces along small x and small y direction at node 1, and these can be replaced by reaction forces at node 3 along small x and small y direction. So that can be written similarly from the free body diagram of, so if I draw the FBD of FBD means free body diagram of node 1. So if I look at the node 1, so this is node 1. The reaction forces in terms of global coordinate directions are already R1 and R2. And then you have, because no, if you look at the element, so at node 1, this is a force on the element. So opposite of this is going to act on the node. So that means when I draw the free body diagram of node, I will have the force in this direction. So this would be Q11. Now in this, if you write sigma fx is equal to 0, so you will get basically R1 is equal to minus Q11 upon root 2. So that is what I was saying, that no, this minus Q11 upon root 2 can be written as R1, that is force along x direction at node 1. So similarly, if you do sigma Fy equal to 0, you will be able to write R2 is equal to minus Q11 upon root 2. So similarly, if you do the, now draw the FBD of node 3. So this is node 3. The global reaction, the reaction forces and global coordinate directions are R3 and R4. And as you see at node 3, in the element, this is a force Q22. So the opposite of this is going to act at node 3. So that is Q22 in the opposite direction. So we will have this force in this direction. This is your Q22. And for this, now if you write sigma fx equal to 0, sum of forces along x direction equal to 0, you will get basically R3 is equal to Q22 upon root 2. And hello, I have a class. कौन अभी क्लास चल रही है? हाँ ठीक. And similarly, now you have Fy, sigma Fy equal to 0 will give you R4 is equal to minus Q22 upon root 2. So that means as far as the forces are concerned, we can replace all the forces in terms of forces along global x and y directions at each node. So that is what we can do. So this is about the all the relations. and no, this is the equation we are going to solve, and these are the boundary conditions. So you already have these boundary conditions. So now if you look at the number of unknowns, so we already know u1 is 0, v1 is 0, u3 is 0, v3 is 0. So the unknowns are this u2 and this v2, and of course this reaction is going to be an unknown, this reaction is going to be an unknown, this reaction is an unknown, this reaction is an unknown, and this is written in terms of p1, this is written in terms of p2. So if you look at the number of unknowns, number of unknowns are u2 v2, and then this reaction, so r1 r2 r3 and r4. So there are 6 unknowns, and 6 equations we already have now in the form of equation number 4. So if you now look at the unknowns, so unknowns are basically u2 v2 r1 r2 r3 and r4, and we have 4 equations. So as usual, first we will solve for u2 and v2, the displacement degrees of freedom. So that we will be taking the corresponding equations. So we will take the third and fourth equation, the corresponding to this u2 and v2, and solve them for u2 v2, and then go back to equation 1 2 and 5 and 6 to get r1 r2 r3 and r4. So say we taking equations 4 3, that is the third equation of fourth equation, and equation 4 4, you will have ea by l, because now if you take the third equation, so the third equation is basically this into u1, which is 0, then plus this into v1, which is also 0. So you will basically get this half and half, which becomes 1, and this 1 by 2 minus 1 by 2, this is actually 0, this is also 0, this is also 0. So we will have only these terms over there. So we will have here 1 0 0 and 1, and then you have this u2 and v2, and the right side we have this p1 and p2 for this particular problem. So the solution is straightforward for this case. So if you solve this, u2 will come out as p1l upon ea, and v2 will come out as p2l upon ea. So in this case, the solution is straightforward. Now we need to calculate R1, R2, R3 and R4. These are the reactions at node 1. These are the reactions at node 3. So now if I take first equation, so from equation 4 1, we will get no ea by l is there outside, and u1 v1 are 0. So if you take the this into u1 is 0 plus this into v1, which is 0, we will have only these terms, this into u2, this into v2, and of course the right hand side is r1. So we will get that equation as ea by l, and then we will have minus u2 by 2 minus v2 by 2 is equal to r1. That term we are writing as r1, as I already explained. So you can write r1 is equal to, you put the values of u2 and v2, which we have got over here. Now this is a u2 and this is v2. So if you put these values, so we'll get minus ea upon 2, you can take out. So you will have p1 plus p2 into l upon ea. So finally you will see that this reaction is p1 plus p2 by 2, whole thing is minus, so there is a minus sign over there. So this is r1. So same from equation 4 to, that is you take this equation, so this into u1 plus this into u2, that is 0, and then we will have this minus 1 by 2 into u2 minus 1 by 2 into v2. u1 and v1, they are 0, and these terms are anyway 0. So you will get finally from this equation as ea by l, and then you have minus u2 by 2 minus v2 by 2 is equal to r2. So if you put the values of u2 and v2, you will get r2 as, r2 is also coming out as minus p1 plus p2 by 2. So these are the reaction forces. Although if you look at this particular structure is a statically determinate structure, so you would be able to actually get these reactions from the static equations of equilibrium. But no, we are solving this from the finite limit. and which is applicable for any either a statically determinate or indeterminate sphere, we will be solving the problem exactly in a similar manner. So this is what is your R2 is coming out. And then now if you look at from equation 4, so now 1 and 2 we have used, 3 4 we have used. So if we take equation 5, you will get this ea by l, no, the way I have demonstrated would be minus u2 by 2 plus v2 by 2 is equal to r3. And if you put the values of u2 and v2, finally we'll get r3 as p2 minus p1 upon 2. And so similarly from last equation, that is equation 4 6, you will have ea by l, and then you have u2 upon 2 minus v2 upon 2 is equal to r4, and you put the values of u2 and v2, so you will get r4 as p1 minus p2 upon 2. So now if you want to check, so this is, so what we have done, we have got the displacement of node 2 along the global x and y directions. We also have got the reaction at node 1 along x and y direction, and reactions at node 3 along global x and y direction. So if you want to check whether no this finite element is giving you correct solution or not, you should make sure that no the equilibrium equation for the whole structure are satisfied. So the whole is the free body diagram of the whole structure I have already drawn over here. So if you look at this, no, this R1, R2, R3, R4, and P1, P2. So this is the, this whole thing. This is the FBD of whole structure. So for this, the structure as a whole, sum of forces along x direction should be equal to 0. Sum of forces along y direction equal to 0, and moment about any point about z axis should also be equal to 0. So that is the equilibrium equations, they should be satisfied. So for the, you can say that for the whole truss structure, so this is more like you kind of do some of these calculation in first year engineering mechanics. So I'm demonstrating that the finite element solution satisfies all those. So BTech first year mechanics. So sigma fx equal to 0 for the whole structure. So if you look at the whole structure, along the x direction one force is R1. Now if you see here, one force is R1, another is R3, and this P1. So these are the forces along x direction. So I should have R1 plus R3 plus P1 equal to 0. So if you put the values, so you have R1 is minus P1 plus P2 by 2, and R3 is P2 minus P1 by 2 we have already done, plus P1. So you will see that this is 0 equal to 0. So this equation is satisfied. So our solution, finite element solution, satisfies the equilibrium of the whole truss structure. Sum of force along x direction equal to 0. Similarly, if you look at the forces along y direction, so we will have R2, R4, the reactions, and P2. And if you put the values, so this must be equal to 0. So basically we will have R2 is P1 minus P1 plus P2 by 2, and this R4 is P1 minus P2 by 2 plus P2 is equal to 0. So you will see that this is 0 equal to 0. That means this equation of equilibrium is also satisfied. So all the equations of equilibrium are satisfied. And similarly, if I take moment about any point, let's say I call this as point A, and I'm just calling node 1 as point A, and taking the, because a coplanar force system, so these are three non-trivial equation. Moment of all the forces about z axis passing through point A, this should also be equal to 0. So we need to check that. So this would be R4, and now you will have the you have to write the, basically if you want to calculate the moment of all the forces about point A. So see this R1 and R2, they are passing from point A, so they will not have any moment about A. R3 is for the given case is also passing through point A, so will not produce any moment about A. This R4 will produce a moment. So this length is L, this length is L. So if you look at no, this length is going to be L by root 2. This will also be L by root 2, and this will also be L by root 2. So the moment of R4 is going to be R4 into L by root 2 plus L by root 2, and moments of P1 or P2 going to be P1 into L by root 2, P2 into L by root 2. So and of course you need to take care of the direction. So L by root 2 plus L by root 2, that is R4, minus P1 will produce moment about negative z axis, so minus P1 into L by root 2. P2 will produce moment about positive z axis, so P2 into L upon root 2. This should be equal to 0. So if you put the values, so you will see this R4 is P1 minus P2 upon 2, and L by root 2 plus L by root 2 would be root 2L, and then we have minus P1L upon root 2 plus P2L upon root 2 equal to 0. So we will find that this is 0 equal to 0. So this is also satisfied. So all the equilibrium equation for the whole truss structure are actually satisfied. So yeah, I think no, I no, I think you have class at 11. So I will stop here. The post processing part I will do in the next class. So that is a calculation of displacement at any point within first element, and then the strain and stress calculation in the first element, strain and stress calculation in the second element, and then cross checking it with the solution which we obtain from what is known as method of joints. So probably you would have studied method of joints in your mechanics course. I will show you how we do that, and then we will show that the stresses obtained from FEM are exactly same as what we will get from the forces obtained using method of joints. So yeah, I want to stop here. Please go through this, and I know, yeah, if you have any questions and doubts, no, you can ask. Yeah, any question, any doubt, anybody? Anybody, any question? Okay, so then I am stopping. Thank you all for your attention. Thank you.
Thank you, sir.